Mastering is the final stage of production when you're making a recording. The last chance to listen, tweak, double check to make sure there's no problems, and make any final adjustments to the completed mix before sending it out into the world. But past that general description, the technical specifics of what goes on in the mastering suite have always been a little mysterious to the average engineer or recordist. Exactly what processing to apply, and more importantly, when and how much to apply, are part of the so-called black art of mastering, which for years was always left to dedicated mastering engineers in their specialized studios full of pricey, high-end equipment that was often kind of unfamiliar to most tracking and mixing engineers. But with the advent of software-based mastering tools, the art of mastering was brought to the masses, for better and worse. Better, because now anyone could own the tools they'd need to handle that final stage of preparation to get their projects ready for distribution, by whatever means. But also worse, because applying powerful mastering processors to a full mix can just as easily have a negative impact on the mix as a positive one, especially if used with too much of a heavy hand. And the ready availability of these relatively low-cost processors, as opposed to the really pricey gear employed in mastering suites in the pre-digital era, doesn't factor in the even more important aspects of what a dedicated mastering engineer brings to the job. One of those factors is his experience in listening for the more subtle aspects of a mix that might need to be addressed, and applying processing sparingly, often doing as little as possible, just what's absolutely needed to serve the music. A professional mastering studio is also an acoustically calibrated and treated room with a set of calibrated monitors that provides a listening reference that can be trusted. A lot of mix rooms, especially smaller, untreated project and home studio environments, they work fine for tracking and even for the broader strokes of mixing, but for the very small, very subtle adjustments to the mix that a good mastering guy will be making, mixing rooms may cull the sound enough that they'll fail to provide a neutral enough reference for those tweaks to translate properly when others play the song in other environments. And that's a big part of what mastering is about, making sure the song will travel well, sound good anywhere. And finally, when a dedicated mastering engineer is handed a song or album, he's bringing fresh ears to the music. No matter how good or even how experienced the engineer who did the mixes might be, he can't hear it fresh the way the listening public will. He's heard it so many times, he's gotten used to all the little quirks on the tracks, and is likely to subconsciously gloss over some subtle issues that should be addressed in mastering. Fresh ears, at least those experienced in listening for detail, will be more likely to pick up on those small issues, and maybe even hear a few areas where something could be improved on a bit. Just because they're able to react to hearing the mix for the first time, things that are flying under the radar of everyone who's heard the tracks 1,000 times will jump out clearly, and subtle tweaks can be made that enhance that initial impression that listeners will get when they hear those songs for the first time. Now, it may sound like I'm making an argument here to always take a project to a professional mastering house, and that is a good idea, if possible. But in many cases, it's not an option. Budget constraints, time constraints, availability, all these are good reasons why artists, mixing engineers, and even home recordists may need to complete that final production stage themselves, so the recordings will stand up, technically, to any other recordings out there. Nobody wants to have listeners distracted from the music because the recording is too soft, or too loud, or too muddy, or too thin, or the image is imbalanced, or the vocal's not clear enough, or any of the other technical flaws that can distract a listener from the music on that critical first listen when most people decide if they like a song and will want to hear it again. So that's what this course is for. We can't put everyone into a calibrated mastering studio or endow them with the years of experience and critical listening skills that those guys may have. But we can provide some guidance for applying mastering inside the box with the tools that we all have available nowadays in our DAWs and third-party plugins. The course will touch a little on the evolution of mastering and cover the technical concepts and terminology, like sampler rate and bit resolution, background knowledge that's necessary for the technical aspects of mastering. There'll be a brief overview of some of the tools available, and I'll also cover pre-mastering, what should be done to a finished mix to prep it for that final stage. I'll go over strategies for organizing an in-the-box mastering session, including issues like mastering a collection of songs, like for an album, and using commercial reference tracks to help get a handle on how your master tracks will sound when they get out into the world. And then, of course, I'll spend the most time going over the various tools that are used in mastering: EQ, compression, including multiband compression, and limiting, specifically the specialized brick wall limiters that are what's used to get recordings so loud these days. I will touch on the loudness wars, one of the big issues facing anyone who tries their hand at mastering, especially for a client. I'll even go over mastering applications for MS, mid-side processing. The course will finish up with a look at the very last stages of a mastering session, final safety checks, and bouncing down, including a little on the various file formats out there. I'll even touch, very briefly, on the embedding of metadata in the finished audio files, the data that's used to track sales for commercial discs and downloads. So while this course won't make you into a seasoned mastering specialist overnight, you'll still have to train your ears and your hands to get used to the more subtle listening and tweaking you need for effective mastering. You should come away with a solid understanding of the tools, the issues, and the process of mastering, and that should put you well on your way to making better masters. So let's get started. In the heyday of analog recording, mastering was primarily associated with the process of technically preparing a finished recording on an analog tape to be transferred to disc for eventual distribution as a vinyl record, an LP. It wasn't really thought of as a creative part of the process, the way some view it now, and it wasn't expected to change the mix, which was seen as finished, to the degree that some people expect nowadays. Changes to the final mix were made to ensure that it would fit properly in the more limited dynamic range of vinyl, and that consumers' record players would track the record reliably and not skip due to any issues within the record groove itself. The process of EQing at this stage was partly to compensate for the frequency response of phono cartridges. A standard EQ curve, the RIAA curve, had to be applied to the recording to be decoded in playback in order to provide a full tonal balance. And expected losses in frequency response due to the transfer to and playback of vinyl media were often compensated for ahead of time by pre-EQing the audio, called pre-emphasis, anticipating the wear and loss that would occur when the finished records were played on home equipment. Excessive bass energy in the tracks, especially if it was mainly on one side of the stereo field, could result in a groove that was problematic enough to cause skipping on some of the more inexpensive turntables. This is one of the issues that led to the traditional practice, still standard even with digital media, of putting low frequencies in the center. There was a trade-off between bass, the maximum loudness of the record, and the running time. If you had a recording with a lot of strong lows, and you wanted a louder level to make it stand out, the loudness wars go back that far, well, you'd have to sacrifice overall running time. If you wanted a longer running side, you might have to compromise on level or low end to cram more music in. These were the kind of technically driven issues that mastering was primarily concerned with in the vinyl era. Maybe the biggest issue was the limited dynamic range of vinyl, more limited than tape, which gave rise to the use of compression to make a recording with a wide dynamic range fit on vinyl. If the quieter parts were cut too low in level, they'd be swamped with record surface noise, the ubiquitous hiss and crackle vinyl lovers are all too familiar with. But if the mastering engineer tried to cut the track too loud, the metal mastered disc could be ruined, an expensive mistake. Or even if he succeeded, some cheaper turntables might not be able to track the grooves, and that record would skip, again, something that could not be tolerated for a commercial release. So, compression was employed to reduce the dynamic range for vinyl, and this gave rise to many of the more specialized features, like MS, mid-side processing, which offers greater flexibility in processing for the vinyl medium. Many of the earliest outboard EQs and compressors were intended primarily for mastering applications, until, of course, multi-track recording and engineers in the 60s and 70s found new creative applications for them. When CDs took over from vinyl as the standard for commercial distribution, questions of EQ curves and limited dynamic range were no longer an issue. Unfortunately, many of the pre-EQ'd, pre-compressed masters, which were never intended to be heard without the limitations of vinyl they were processed to compensate for, were mistakenly used for a lot of early digital CD releases. The resulting thin, nasty sound was one of the things that contributed to early digital audio's initial bad reputation among more discerning ears. Eventually, all this was sorted out. But, ironically, the wider dynamic range of digital media started to be utilized less and less in favor of the quest to make recordings ever louder, something which could now be achieved to a much greater degree with the software-based processors that started to appear. The mastering stage gradually transitioned from a purely technical exercise to a combination of technical and creative applications. Modern mastering tools could remove noise, change balances, and compensate more effectively for questionable mixing choices. And the old industry joke, whenever there was a problem in a recording, "Oh, well, we'll fix it in the mix," started to morph. When a finished mix had minor flaws, it became, "Oh, well, they'll fix it in mastering." People started to think of mastering as some magical panacea for any problems, technical or aesthetic, that slipped by in the earlier stages of tracking and mixing, resulting in what were sometimes unrealistic expectations of just how much the mastering engineer could really do. And then, as the loudness wars took hold, the crazy race to make each new release as loud or louder than everything that went before, in a misguided attempt to draw attention, mastering started to become known as the step where you make it loud. Of course, the real value in mastering nowadays is the ability to address a host of minor issues that, if dealt with effectively, can subtly improve the presentation of the music. Not by making it louder, or more this or that, but by making the technical side as transparent as possible, so listeners aren't subconsciously distracted by subtle flaws in the recording and are able to focus solely on the music. But to accomplish this, you still need to be familiar with the underlying technical concepts. So next up, I'll go over the basics of digital audio for a little of that necessary background. Since this course will be dealing with mastering in the box, in the digital domain, I'm going to include this tutorial on the basics of digital audio just for completeness. It's only a brief overview. You can find more comprehensive explanations of all this elsewhere on the site, like in the Audio Concepts course on recording tools. I'll go over the basics here, but only in the broadest strokes, and with the emphasis on the terminology and concepts that you're likely to run into when using mastering software. If you already know all about sampler rate, bit resolution, and file formats, you can just jump ahead. As most everybody knows by now, digital audio files are made up of a string of binary numbers, ones and zeros, that describe the changing shape of the audio wave. While digital recording tools had some design flaws in the early days, modern digital recordings do an excellent job of capturing and preserving the shape of audio waves. Any remaining limitations are outside the range of human hearing. Audio processors, the DAWs and plugins, recalculate these numbers to deliberately change the audio waves, to change the sound. That's how all processing, including mastering processing, is accomplished. To create a digital recording, the original continuous audio wave is captured, first electrically by a mic, and then sampled at discrete points in time as the first step in digitizing. This is done because you can't numerically describe a continuously changing wave, but you can numerically describe one that changes in steps by assigning a number to describe the different level of each step. And that's what sampling is. The key is how many samples you take per second, the sampling rate. If you sample at a high enough rate, take enough samples per second, then you'll capture all the audio frequencies we humans can hear. And if you follow the sampling rule, the infamous Nyquist theory, your playback devices will be able to restore the smooth shape of the original wave with perfect accuracy. Despite urban myth, nothing is lost from sampling as long as the minimum sampling rate and Nyquist rule are adhered to. The recording industry has standard sampling rates of 44.1 kHz for music or 48 kHz sound for video. That's 44,100 or 48,000 samples per second. You'll see options for higher rates, double and quadruple 44.1 and 48K. You can use these, and many engineers swear by them, as being subtly better sounding, though the differences when audible are subtle. Some plugins can process the audio at higher rates than the session and completed files. In some applications, this can be, again, subtly beneficial. Generally, the choice of sampler rate follows whatever practices are most common for the genre of music you're working in. So if you're mastering a rock or R&B track, it'll be likely to come in at 44.1, and that's fine. If you're asked to master a more acoustic, less processed mix, like a classical or jazz recording, then you'd most likely find yourself with a higher sampling rate. 96K is the most common. Some people upsample a recording to a higher rate for the final stages. Others feel this doesn't offer any real advantages. Questions of what's the optimal sample rate are actually a contentious subject among engineers, so if it comes up in a commercial mastering job, it's best to take a practical view and stick to the old adage, the customer's always right. The other aspect of digital recording is the bit resolution. When an audio wave is sampled, the level of each sample must be described as accurately as possible by a binary number. The binary system can be implemented for greater accuracy electrically. That's why it's the basis for all computer files and calculations. The process of assigning binary numbers to describe sample levels is called quantization. The more binary numbers that are available to describe each sample, the more accurate each description can be. If enough are utilized, then any residual inaccuracy will result in distortion outside, below, the range of human hearing, and the recording will sound, and be, for all practical purposes, perfect. The range of binary numbers is determined by the bit resolution of the system. Each 1 or 0 in a binary number is a bit. More bits equals higher bit resolution, equals more accurate files, equals better audio quality. CDs were standardized at 16-bit resolution. While this is good, the inaccuracies, the inherent digital distortion, is not completely inaudible, so digital designers actually added random noise at very, very low inaudible levels to 16-bit recordings to smooth out any possible low-level flaws, even though these would be mostly perceived subconsciously, if at all. This noise is called dither, and if you're making a 16-bit master to be used for CD duplication, you still must add this dither signal into the final bounce. But all other audio masters should be made at the current standard of 24-bit resolution. At this resolution, any inherent limitations or distortions are inaudible to human hearing, so no dither is needed. So, all your masters should be at 24-bit resolution with no dither, but if needed, a separate 16-bit bounce should also be done with dither for CD duplication purposes only. Now, all of the numbers I've mentioned assume that the audio file format is LPCM, linear PCM, pulse code modulation, the standard for full quality digital audio, WAV or AIF audio files. But, as you all know, there are other formats out there as well. MP3, MP4, AAC. These are smaller files, anywhere from a fifth to a tenth the size of PCM audio files, and they're ubiquitous. Their smaller size makes them ideal for reliable streaming and fast downloading, but the audio in them has been audibly compromised to achieve their smaller size. Even the best of them are subtly thinner sounding with less clarity and punch, so while you may have to make them and use them for convenience, all original masters you make should be in PCM format, ideally WAV files, and only these full-quality masters should be used for any professional applications. And MP3 and MP4 AAC files should not be used as references for your mastering efforts. Only PCM files can provide a suitable full-quality reference. So, this was a very brief overview of digital technology and terminology, as it might come up in mastering applications. Again, for a more comprehensive take on any of these subjects, well, you know where to go. But for now, I'm going to move on to an overview of mastering gear, and then a look at mastering strategies. Naturally, mastering started out in the analog domain, with individual EQs, compressors, and other hardware devices hooked up in a chain for processing, with the results eventually printed on a master tape and cut to a metal disc master for vinyl pressing. Even today, professional mastering suites often incorporate a collection of high-end analog processors, again, EQ and dynamics primarily, along with their digital tools. High-end speakers and amplifiers are chosen for their accuracy and transparency, and additional reference systems may be available to more closely approximate all the different playback systems and formats that modern listeners are likely to hear their music on. There are plenty of analog boxes that may be employed to good effect in mastering. A lot of these would come under the umbrella of character processors, devices that impart a characteristic analog quality, which is often desirable. These include various tube and solid-state EQs and compressors. Many people like to run digital audio through analog circuitry just to get the sometimes beneficial effect of that circuitry, hopefully a warming presence, that may be lacking in the cleaner, more neutral digital signal path. analog summing boxes are often used for this purpose, as they are in mixing. There are also a lot of dedicated analog mastering units, and though most of them are pretty pricey, they all provide the quality and feature set needed to achieve professional-level mastering results. Often, an artist may want to try rendering the final master both digitally in the box and to a stereo analog tape recorder for the inimitable warmth and edge that medium provides. In larger mastering suites, it's not uncommon to do both, and then compare them, sometimes song by song, to see which songs benefit from the extra analog warmth and which fare better in the cleaner digital version. For those who try their hand at mastering in their own studio environment, big or small, while there's always the option of incorporating analog gear, especially if that gear is already there, most mastering nowadays will probably be carried out in the box with plugins or dedicated mastering applications. Every DAW has EQ and dynamics, and most include at least some dedicated mastering plugins. Logic, for example, which I'll use in a lot of these videos, has a mastering EQ, a multiband compressor, a brick wall limiter, and a collection of metering plugins, all providing suitable processing for mastering right out of the gate. And there's no shortage of dedicated third-party mastering plugins. Both individual processors and bundles are available from companies like iZotope, Waves, Wave Arts, IK, Sonux, UAD, Sony, Steinberg, and a host of others. Many are even very reasonably priced. For example, iZotope's Ozone, in its most basic version, is an entire mastering suite for under $250, and Massey offers very inexpensive tools, like its well-regarded L2007 mastering limiter, in free, limited feature versions as well. Even simulations of analog tape are up to snuff nowadays, from players like Waves and UAD, among others, for those who still want that sound, even while they stay firmly ensconced in the box. In these tutorials, I'll demo with a number of different software mastering tools, including the ones that come with Logic and Pro Tools, and the iZotope Ozone collection. But first, a look at what to do to prepare mixes for mastering, the final pre-mastering stage. While some engineers may like to apply mastering processing during the mix stage, most would probably agree that it's better to treat mastering as a separate session. In fact, as I mentioned earlier, many prefer to have a different engineer handle the mastering who hasn't heard the tracks 1,000 times already. The mix engineer, producer, and artist have gotten so used to hearing the mixes that they're likely to miss or gloss over little details that might need fixing or just might benefit from a tweak here and there. But if you've recorded and mixed some music and still need to do the mastering yourself, that's still fine. You just have to make sure you don't try to tack it on at the end of a long mix session when your ears are already tired and the song is already swimming around in your head. Whenever possible, it'd be best to take as long a break as you can before starting the mastering session, even a day or two ideally. Then you can bring slightly fresher ears to it, and you will notice details that you'd probably have glossed over when the mixing stage was still fresh in your mind. But before you're ready to sit down and start pulling up mastering EQs and limiters, you want to prep the mixes and organize the mastering session, especially if you're mastering a group of songs. I'll start with prepping the mixes, sometimes referred to as pre-mastering. There are a number of considerations that come up when you're wrapping up a mix and getting ready to master it. One of the biggest issues is whether to use bus processing in the main left-right stereo bus, the master fader in Pro Tools. By this I mean, should you strap an EQ and compressor across the main stereo output, processing the entire song as part of the mix stage, or leave that kind of overall processing strictly for the mastering stage? Now, this is an area where many good engineers often disagree. A lot of people not only add master bus, EQ, and compression to the mix, but they wouldn't do a mix without it. Many others feel this is a dubious practice, that a mix should stand on its own without the need to use overall processing, that should be the domain of the mastering guy. If you ask mastering engineers about this, I think the majority of them would probably say they prefer there be no stereo bus processing done. The more aggressive the bus processing that's applied in the mix, especially compression, the less control the mastering engineer is going to have to deal with any issues he may need to address. Personally, I find myself in the latter camp. I think a mix should work without needing bus compression, and I feel that mixes should be supplied to the mastering session without any applied. However, since modern mastering practices do have the potential to alter the balance of the mix, especially how the drums sit in the mix, I always run a mix through some mastering plugins with appropriate settings to anticipate any issues that more aggressive mastering processing might introduce. If I feel it might be necessary, I can make tweaks to an alternate version of the mix to compensate in advance for any expected issues. But when it comes time to finalize the mix, I'll bounce the original mix and the mix with tweaks addressing possible mastering issues, and maybe even the mix with my mastering settings applied. If someone else is handling the mastering, I'd send him all these mixes clearly labeled. The main version without bus processing, the version tweaked for potential mastering issues as an alternate, and my mastered bus-processed version as a reference only to suggest what I think the mastered version should sound like. Then I trust the mastering engineer to be able to use his more dedicated tools and experience to do the best possible job of achieving that sound. And if I'm going to master it myself, I take the least processed original version of the mix and start applying mastering tweaks in a separate mastering session after a suitable break from the music, and then use my original ideas as guidance as I make the final choices for the mastered file. Now, most commonly at the mastering stage, the mix has been bounced down to a single stereo audio file. All the decisions about panning, instrument and vocal balance, and individual track processing have been made. The mix stands on its own, and now that audio file is ready to be run through mastering software. Now, while powerful mastering tools and techniques like multiband compression and MS processing can slightly alter the balance of things like vocal level, overall ambience, or bass, changes like that should not really be expected from mastering. If significant adjustments of that sort are needed, ideally the mix would be redone, tweaked for whatever minor alterations the mastering processing may have revealed to be necessary. But sometimes this could be inconvenient. So to give the mastering engineer a little more control over individual elements of the mixer might provide not just a stereo bounce of the finished mix, but also individual groups of tracks called stems. These are still fully mixed with all effects and processing, but the arrangement is broken up into musical groups. Separate audio file bounces of all drums, all guitars, all background vocals, all lead vocal tracks, etc. Together, it's the same mix, but if mastering tweaks make the guitars stick out a hair too much in the mix, or cause the vocal to be slightly buried, it's a simple matter to adjust the level of that stem to compensate. Now, some mastering engineers don't like to work with stems, feeling it's not their place to, in effect, remix the song. Others might welcome them. Generally, though, a simple, all-inclusive stereo mix of the full arrangement for each song is the norm. What has been common for many years, though, is to make up a couple of slightly different versions of the full mix. I mentioned earlier how I might prepare versions with and without bus processing. Another common thing is to bounce vocal up and vocal down versions in addition to the primary version of the mix. Just as it sounds, these would be the same mix, but with the level of the lead vocal adjusted. The main bounce would have the vocal level balanced at the level the mix engineer thinks is perfect. Then another bounce would be done with the vocal level raised up very slightly, and a third with the vocal level down very slightly. Never more than a dB, more or less, than the original version. The idea has always been that if mastering compression or EQ changes the way the vocal sits in the track, making it seem just a hair too loud or soft, then simply switching to the vocal up or down version will compensate and save time. So it's likely that walking into a mastering session, each song may be available in several different versions. Most mastering engineers would start with the one that's been labeled the main mix, the primary version, and utilize others either as a reference for the mix engineer's suggestions or intentions, or to compensate for any unintentional changes that are brought about by the mastering processing. Next up, I'll go over setting up for a mastering session. To organize a mastering session, naturally, you'd first assemble all the finished mixes and any other versions, references, alternates, stems, whatever. I'd identify the main version and then create a new session in whatever DAW or application I'll be using. I'll do this in Logic. If there are different versions of the full mix, I'd bring each one in on its own stereo track. If there are stems, I do the same, but then bust them all through a stereo aux where I can apply overall mastering to the full mix. I'd mute and even maybe hide all the tracks except the main one, coming back to them if I feel I need to use them as the session progresses. If there's a version with suggested mastering processing on it, I might choose to listen to it initially as a reference, especially if it's my own mix. But more likely, I choose to approach the song fresh, play through the main mix and begin working on it, using my, hopefully, fresh ears as my guide. I'd instantiate whatever mastering plugins I plan to use on that main mix track. Since I might want to try alternate settings, or alternate plugins, I won't put them on the session's main stereo output channel, but on the individual tracks for each mix I'm working on. This is kind of up to you, but I'd recommend it for greater flexibility. Of course, if the session involves mastering more than one song, then having individual chains of mastering plugins for each song gives you the flexibility you'll need to tweak each individual song appropriately, even if the settings for each tune start out the same. If the DAW has any kind of automatic plug-in delay compensation feature, you want to make sure it's turned on. If you're unfamiliar with that, I'll explain briefly. Most real-time plugins can do the calculations they need to do for processing without having to delay the audio playback. But some, especially ones designed to maintain the highest possible sound quality, may cause the track they're on to be delayed in real-time playback by several milliseconds to allow time for their more intensive calculations. This is called plugin latency, and mastering plugins are notorious for introducing significant delays. In a multi-track setting, this can be a problem, so most DAWs have a feature that automatically compensates for any such delays. Now, processing an individual track with a single stereo mix on it, musical timing is not an issue, but if there is plug-in latency, any bounces may reflect that with a slight gap at the beginning of the newly bounced audio file, so it's usually best to have this feature on to avoid that. But every DAW handles this a little differently, so if there's any doubt, you should check the DAW's documentation and determine what the best option is. If there are multiple songs being mastered, a collection like for an album, then you'll want to place each one on its own track with its own chain of mastering processors. Probably the same chain for each one to start. You could either line them all up starting at bar 1, or offset them in the projected order they might be in on the completed album. The latter approach makes it easier to get a sense of how the songs may flow one into the next. Making sure those transitions aren't unintentionally jarring is an important aspect of mastering an album. One of the extra responsibilities of mastering a collection of songs is to ensure that they all share the same overall balance and tonal quality and are musically consistent in level. You don't want a listener to be distracted by technical matters as he or she plays through the album, because one song is much brighter or bassier than the previous one, or because the overall level of a soft ballad without drums is much louder than the overall level of the next high-energy song, making what should have been its musically dramatic entrance anticlimactic. If all the songs were recorded and mixed at the same studio, with the same artist and engineer, then this is usually a matter of subtle tweaks from song to song, or what'll probably be basically similar settings on all the tracks. But if the songs were recorded and mixed at different studios, by different engineers, or if the album is a compilation of different artists, then it'll be a lot more work to get them to flow seamlessly from one to the next. That'll be a big part of that mastering session, and you should anticipate it taking quite a bit longer. Once I have all the songs to be mastered laid out on individual tracks, and all the processors at the ready, I'd add a few more tracks and load in some additional reference tracks. These would be commercial releases to be used as a reality check while the mastering session is progressing. I'll cover that in the next video. One of the goals of a mastering session is to make sure that if the finished songs are heard in rotation on the radio or in a playlist, there are no technical flaws that distract listeners from focusing on the music. If one song jumps out at the listener too much because its average level is much softer or much louder, or because it's distractingly brighter or duller than other songs, or for any number of technical reasons, the momentary distraction can take a listener's attention away from the music just long enough to pull him out of the zone, so to speak. The result can be a subconscious negative reaction to the song, even though it wasn't the music itself the listener was reacting to. Now, of course, besides the music itself, every song is technically going to sound a little different, in tone, in texture, in ambience. But a tune whose sound quality is too far off the average can jar the listener and subconsciously sound wrong, at least for the first critical few seconds. Of course, the ear adapts eventually, but the listener may never be as fully absorbed in the song as they would have been if they were pulled in from the very beginning. So it's important for the mastering engineer to ensure that, while every song will have its own unique tone and balance, it's not so far outside the expected norms that it breaks the listener's focus on the music itself. Unfortunately, our ears tend to adapt to different sound quality gradually, so if we were to master a tune that was very bright and somewhat thin-sounding, and noticeably lower in level than most other songs, as we were working on it, our ears would become accustomed to that level and tonality, and we might not realize we'd gone a little too far with the EQ or compression. We'd hear through the overall tonality to the song itself, focusing on other positive aspects, like clarity and detail, maybe. But another listener, hearing that song streaming in a playlist for the first time, might react negatively, and again, subconsciously ascribe that reaction to the music itself, forming a negative opinion of the song. With experience, mastering engineers can develop a good sense of what the acceptable range of differences in sound quality is for various songs. But like any ear training, that kind of internal reference takes some time to develop, and if you're tired, or if the sound of a mix is a little off, it's easy to become accustomed to that sound and not realize how it might hit other first-time listeners. To deal with this, it's a good idea to have some well-mixed, well-produced, well-mastered commercial reference songs available for occasional A-B comparison during the mastering session to serve as a reality check. How will my work, how will this song sound when it's heard in the context of other well-produced songs? These can be loaded into other tracks in the mastering session, and when you want to get a sense of where you're at in terms of EQ, dynamics, and level, you can quickly A-B the song you're mastering against a few of the reference tracks. Now, it's important to note, you shouldn't necessarily be trying to exactly match any one of them in terms of tonality, density, and other specific qualities. In fact, they'll all probably be noticeably different from each other, but they'll also probably all fall within a certain range of brightness, fullness, dynamic range, and loudness, and you'll want your mastered song to also fall within that range as well, so when it comes on after some other tune, the only thing that attracts the listener's attention is the music itself, giving it a chance to pull the listener in without fighting any subconscious negative reaction to a sudden, unusual, and distracting difference. For this A-Bing against reference tracks to be useful, you need to set up the references properly. First, they should all be full-quality linear PCM audio files, WAV or AIF files. MP3s, MP4, AACs, even the best of them have somewhat thinner, more compromised audio quality, so they make for unsuitable references if you want the best you can get. Full-quality PCM files can be pulled off CDs, even though they're only 16-bit and not up to the current 24-bit standard. For this purpose, they'll be fine as reference tracks. Any other PCM or lossless recordings you can find, like FLAC files from some of the high-res audio sites, will also make good reference tracks. You'll want each one on its own track in the DAW with no processing on them, and since when you A-B two audio files, the louder one always initially seems to sound better, you'll want to match up the playback level of the reference tracks to the level of the song you're working on, so you're comparing apples to apples in terms of average overall level. You can do this by ear, but try to get them as close as possible. It'll make A-Bing far more helpful. However, when the mastering processing is almost done and you're ready to set the final overall level of the new song, then you should reset the levels of the reference tracks to unity gain, 0 dB on their channel faders, so they can serve as references to measure the overall loudness of your mastered songs. The reference tracks should all come from recordings with the best quality. I've often chosen songs that won Grammys for production or mastering, and they should be in the same genre as the music you're mastering. Ideally, you'd have about 3 or 4, and the best thing would be if they all had slightly different tonal balances and overall levels to establish the range you're shooting to fall within, without pushing you to focus on one particular sound quality, bright, warm, whatever, too much. You should set up your DAW's solo function so clicking one solo button will unsolo all the other tracks to facilitate the A-B switching. Then, as you're working, you can periodically pause for a quick reality check, just to keep your ears honest. Now, I said before that it's not necessary to try to make a new mastered song exactly match the tonality of any particular reference tune, just to be in the ballpark. But there is one situation where you might want to try to match the tonality of a reference track more closely than just in the ballpark. If you're mastering a song to be included in a collection, you might want it to sound like it was recorded and produced in the same sessions as all the other songs on the album. That would fit with most listeners' subconscious expectations when playing through an album. I'll address that a little when I talk about extra mastering techniques near the end of the course. But for now, just making sure your masters don't stand out in a negative way is one of the goals you'll want to shoot for, and having good reference tracks available can be a really big help with that. Next up, the tools of mastering. Once a session's been set up, the audio's in place, maybe some reference tracks in there as well, then it's time to turn to the processing. The mainstays of most mastering chains are EQ, compression, and limiting, occasionally supplemented by some other processors. These can be either analog or digital, but since this course is mastering in the box, I'll focus on digital, software tools. Let's start with the main three. Naturally, EQ is a frequent component of a mastering chain, but while some fairly drastic tonal variations are typically made with EQ when it's used on individual tracks in a mix, it's usually used much more subtly in mastering applications. Unless the mix has major problems, typically only a few dB of adjustment at most should be needed. Different types of EQs can be employed, from standard designs to character EQs to special linear phase EQs targeted toward more subtle mastering applications. I'll cover all these in the next chapter when I start going over the individual processors. Dynamics are, arguably, the most key aspect of mastering processing. As I said earlier, even though many engineers like to employ bus compression on the mix itself, most mastering engineers prefer it if that step is left to them, especially when mastering a collection of songs. The more dynamic range the mix has, the more control there'll be to adjust dynamics to the needs of the mastering session, for consistency with industry norms or other songs in the same album or collection, for example. Compressors in mastering can be the same ones used for mixing, general purpose models, classic designs with their own sonic signatures, or, commonly, powerful multiband compressors, which offer greater control over the effect the compression has on the different instruments and elements within a full mix. I'll cover compression, especially multiband compression, in detail as I go through the processors. Still in the realm of dynamics, the last processor usually applied is a limiter, specifically a brick wall limiter. This is a hard limiting device that was originally used simply to prevent any digital overloads, but is now employed to also allow the average level of the mix to be raised to much louder levels in comparison with other songs' levels than was possible before the advent of digital limiting tools. This has given rise to the infamous loudness wars, the race to make each newly mastered song as loud or louder than all others, supposedly to draw a listener's attention to it. This contentious practice has become a major part of mastering, and it has to be addressed carefully to avoid compromising the mix quality. I'll go over the use of brick wall limiters, also known nowadays as loudness maximizers, in detail as well, along with a discussion of the loudness wars and how to deal with the issues that brings up. Though they don't actually affect the sound itself, metering plugins are useful to provide valuable technical information, especially in the final technical check, to ensure that there are no unnoticed problems slipping by, like phase issues or stereo imbalances. Some mastering suites also include additional processors that, while not utilized regularly, might come in handy once in a while. For example, iZotope Ozone incorporates an exciter and an imager, along with the usual components, for occasions when the high end may be lacking, or the stereo width of the mix might require some adjustment. Though they're not usually bundled with mastering suites, audio repair processors, like the modules of iZotope's RX, may sometimes find their way into a mastering session. If the mix has a flaw that can't be addressed with the usual processes, like too much reverb or a background noise that somehow slipped through unnoticed prior to mastering, these powerful tools might be called into play to deal with the problem. That sort of thing might be dealt with prior to mastering, but if it does come up during mastering, having such tools handy might just save the day. I'm not going to focus on repair in this course. It's covered well in other courses, but I did want to give it a mention. Now, people always ask, what order should the processors go in? Well, other than the brick wall limiter being last, except for dither when applicable, there are really no hard and fast rules. In a mix, I tend to put compression ahead of EQ, so if I make large EQ tweaks and the overall level of the signal changes, I won't have to reset my compressor's threshold constantly to compensate. But when mastering, since the EQ tweaks are usually much more subtle, a dB or so, they shouldn't cause drastic overall level changes, so I tend to place the EQ ahead of the compression. Actually, when mastering, I tend to rely more on multiband compression, which can function as a kind of dynamic EQ rather than relying on traditional static EQ, which I might not use at all. But this all depends on the sound of the mix going in and the particular tools available for the session. So let's start looking at those tools in more detail, starting next time with EQ. I'm not going to cover the basics of EQ here. I assume if you're ready to try your hand at mastering, you're already familiar with the use of EQ in recording and mixing, and the basic configurations like graphic versus parametric, or peaking versus shelving response. Instead, I'll focus more on the different types of EQs you might find, and the differences in approach you might take in a mastering situation as opposed to recording and mixing use. First off, while there are dedicated mastering EQs out there, any EQ can be used for mastering purposes. Since we're talking about mastering in the box, I'll break them down into 3 types of EQ plugins you're likely to come across. Standard EQs, like the kind that are included with every DAW, basically channel EQs. Character EQs, which are designed to sound and behave like analog circuits, usually vintage analog designs like tube-based models or passive EQ designs. And linear phase EQs, which are often bundled with mastering suites and targeted at applications where clarity of sound is prized. Now, none of these is necessarily the best in every situation, despite what marketing might sometimes suggest. They can all serve well for mastering use. But they all will sound different, even with identical settings dialed up. In fact, pretty much all EQs will sound different, even if they're of the same type, just due to specific differences in design. If you use EQ for recording and mixing, then you already knew that. Character EQs are designed to capture the sound of analog circuit designs. This means that they will, by design, impart their own sonic character on any signals running through them. Sometimes, even when you don't dial up any boost or cut. They're often based on classic analog EQ designs like the venerable Pultec EQP-1A, a passive design with tube circuitry known for its inherent analog warmth. This EQ is one company's take on that Pultec model. Now, a lot of the time, in mastering, you want your tweaks to have as subtle an effect as possible in the mix. But that doesn't mean you can't use this kind of EQ to impart a little warmth. You don't have to dial up drastic settings. You don't even have to dial up as much of an obvious change as I've done here. If the plugin is well designed, the subtle flavor of a typical character EQ should come through even with minimal processing. Now, the standard type of EQ you'll find, and probably will get used the most, is the typical channel EQ that comes with every DAW. By design, these are sometimes referred to as minimum phase EQs. I'll explain that in a minute. These general purpose designs are fine for any application, from recording to mixing to mastering. In a lot of mastering suites, you'll often find a linear phase EQ. The idea is that this type of design will be more transparent than a standard minimum phase EQ. Okay, a little explanation. All analog EQs, and most digital EQs, produce phase shift when you dial up a boost or cut. Phase shift delays the frequencies just above and below the center frequency, affecting the harmonics in that range, and subtly altering the tone over and above the intended tonal change you're trying to achieve with your EQ settings. This is normal. It's not inherently good or bad, and we're all used to it from using traditional EQs. But some digital EQs employ extra processing to compensate for this artifact, eliminating the usual phase shift. These are your linear phase EQs. Without the usual phase shifts, these EQs may, in fact, sound more transparent, especially on already mixed material, like you'd be processing in a mastering session. In some cases, they might allow you to dial up a subtle tonal change to part of the frequency spectrum with as little effect as possible on other areas of the mix. That's one reason they're often included with mastering bundles. But they do come with some caveats. The extra processing, to compensate for the phase shift, results in higher latencies. And a side effect of that compensation is that a linear EQ may, if used more heavily, soften transients a little. But with small tweaks, as I've suggested are most appropriate for mastering, the differences between regular minimum phase and linear phase EQs are small and subtle. Either can do a good job. Ultimately, your ears will be your guide. Next up, I'll compare these different EQ types and talk a bit about general EQ usage in mastering. Now, I've mentioned several times already that unless there are drastic, obvious problems with the overall tonality of a mix, the EQ you'd apply in mastering would normally be much more minimal, subtle, than what you might typically do during a mix. Those 10 dB boosts or cuts that can add some sparkle and punch to individual tracks like drums and guitars would result in way too much of the same effect on multiple instruments in a track where everything's already mixed together. Most of the time, if a mix is basically well balanced and not too noticeably bright or dull, or thin or tubby, I find that a dB or two here and there can have a subtle but significant effect on the overall tonality. If there is a problem element, like a kick that's too prominent or a vocal that's not quite cutting through, I might try a little more, maybe 3 or 4 dB at most. But there are other ways to address those kinds of issues that may ultimately work better than EQ, with less need for tonal compromise. Remember, if you add 3 dB of presence to, say, try to bring up a vocal, you may also be adding presence to guitars that are already as forward as they can afford to be in the mix, trading one problem for another. For bigger problems, I might turn to multiband compression, MS processing, swapping out a vocal up or down version, if available, or even, in a pinch, asking the mixer to revisit the mix and make a slight tweak. Personally, I try to reserve EQ for slight adjustments to the overall balance between high and low end, crispness and fatness, and the all-important mid-range, where the clarity of the arrangement is determined. But watch out, it's very easy to add a little top end, say, and then when you like the extra clarity, well, add a little more, and so on. Our ears adjust to the new balance, and it's easy to go overboard. That's why I always have an extra track with the mix that has no processing on it, that I can A-B with the one I'm working on. Again, as a reality check, so I know just how far away from the original I've come. Remember, that original mix was your or someone's idea of exactly what that song should sound like, and if the mixer's done his job well, you shouldn't need to get too far away from that. I'm looping a short section of a mix here, and I have the same mix on 4 tracks. The first one, Brown, is the original mix as is, no processing, as a reference. Below that is the same mix with a character EQ, green, a standard minimum phase channel EQ, blue, and a linear phase EQ, in red. I'll play the original first for a minute. Now I've added more or less the same EQ with each of the different types, around 4 dB of high end for sparkle and 3 dB of low end to balance that out for thump. Now I think this is a lot, too much really, more than the original mix needs, but for the sake of comparisons I want to make it obvious. So first, here's the character EQ. This plugin is modeled after the Pultec EQP1A, a passive tube EQ that's famous for its analog warmth and presence. Now I said I thought this was more EQ than needed. Let's go back to the original mix for a moment. Notice how, now that our ears have become accustomed to the brighter, fatter EQ'd sound, the original version sounds kind of dull and mid-rangey. But in fact, this original balance is much closer to the overall balance of a lot of commercial releases in that genre, and this EQ'd version might sound a bit too processed, a bit too hyped in the high and low end for this style, even though it may seem better at first blush. There's a tendency to always prefer the louder and brighter version when comparing, but after extended listening, a more subtly EQ'd master might work better for the music. I'll reduce the EQ by a couple of dB. This still adds some sparkle and punch, but doesn't sound so processed. Now remember, I'm only looping a short section to save time, but you'd need to eventually play through the entire song when you make tweaks. What sounds perfect in one section might reveal problems in another. The third track here is a standard minimum phase EQ, and the fourth is the same EQ, same layout, but with a linear phase design. Let's compare them. Again, maybe a little bit more EQ than needed, but for comparison purposes. You can hear that the standard EQ seems to have a bit more overall effect on the track, even though the settings are identical. I'll compare each with the original flat mix. Notice how, while they both emphasize the snare and hi-hat as intended, the phase shift in the standard minimum phase EQ slightly emphasizes the guitar as well, whose harmonics fall in the range around the high-end 6K center frequency where the phase shift occurs. The linear phase EQ doesn't affect the guitars quite as much. They stay closer to the way they sound in the unprocessed mix. It's subtle, but it's there. That's why linear phase EQs are often targeted toward mastering use. But on the other hand, you might prefer how the channel EQ also adds a tiny bit more of something to the guitars. Again, either works, it's a matter of preference. Next up, the specialty application, matching EQ. When you're mastering a collection of songs, like for an album, it's important that the songs fit together, not only from a musical standpoint, but from the standpoint of sound as well. You want them all to be well matched in terms of level, overall dynamics, and especially overall tonal balance. It could be very distracting if one song had, say, a very bright overall balance, and another had a much warmer balance. Heard on their own, either mix would sound fine. Tonal balance can span a pretty wide range and still sound good. But if a listener plays through a collection, and, say, a more mellow-sounding mix with strong bass comes in after a fairly bright and tight-sounding one, it might seem too tubby and muffled to ears that have adapted and become accustomed to the previous song's tonal balance. After a bit, the listener's ears will become accustomed to the new balance, but the initial subconscious impression of the song may be negative, and you want to avoid that. Transitions from one song to the next shouldn't jar the listener. We can't control that for radio play, but we can when assembling an album or collection. Most of the time, you'd simply use your ears to tweak whichever song you think doesn't sit well enough with the rest. But some EQs have a feature that offers a shortcut to make this often tweaky task more efficient. This is called matching EQ. The idea is pretty straightforward. The same EQ processor is used to analyze the tonal spectrum of two audio files, a reference song and a target song. The reference will be a song that has the desired tonal balance, and the target will be the one that you want to EQ a bit to make it a better tonal match for the reference. When both have been analyzed, the matching EQ then applies an EQ curve to the target that's the difference between the two analyzed curves, bringing it closer to the reference in overall tonal balance. Logic comes with its own matching EQ. Ozone also includes a matching EQ feature in its EQ module. I'll demo with the Ozone EQ. If you enable the matching function, you'll see places to record the analysis for both the reference and target songs. The EQ is on the target track, so I'll temporarily move or copy the reference file to that track and capture its tonal signature. Usually around 10 to 20 seconds is sufficient. Then I'll capture the sonic signature of the target. Now, when I turn matching on, here, a difference curve will be applied. But this never makes for an exact match. Different songs, different sounding instruments means that you'll still have to use your ears to get the best match. Most matching EQs have a couple of adjustments for this: a smoothing control and a control to set the depth, the strength, the amount of the applied EQ curve. Smoothing makes the matching curve less spiky, hopefully making the tonal adjustment less potentially peaky sounding, depending on the particular songs. And depth can range from just a little of the difference curve being applied to applying it full strength. Full strength is usually too much. When I've occasionally used matching EQs, I've found that around 50% on both of these settings is a good starting point. Here, a slightly less aggressive application of the difference curve seems to sound best. A matching EQ can be cool. In fact, it can be a real time saver on individual instruments in a mix, like for quickly matching different takes in a comp. But I wouldn't expect miracles in a mastering situation. It's a good tool to help you get the EQ where it needs to be, but ultimately, you'll still have to rely on your ears. Next up, I'll move on to compression. Dynamics, compression, and limiting are, I think, one of the most key aspects, maybe the most key aspect, of mastering. Even though ample compression has probably been applied to individual tracks and groups in the mix, this is where it's applied to the overall mix, to use a popular expression nowadays, to glue all the elements together, so to speak. And also, of course, compression in mastering is applied to accomplish its original purpose, to control the overall dynamic range of the song, not because modern media have a limited dynamic range like vinyl did, but to provide a more consistent and enjoyable listening experience in a variety of listening environments, from the ideal to the not-so-ideal. I mentioned earlier that a lot of mixers like to apply stereo bus compression in the mix stage, rather than wait for the mastering stage. Some are adamant about that being part of their methodology, even though most mastering engineers prefer to get a track with little or no overall compression. I won't rehash the entire argument again. I fall into the camp that feels that the more dynamic the mix is, the more flexibility there is in mastering to control dynamics properly without having to fight what's there or try to undo some excessive or inappropriate squeezing added in the mix stage. So, for this section, I'll assume a mix with a reasonable natural dynamic range, compression applied to various elements, but not yet overall, or at least not excessively. As we know, standard compressors reduce dynamic range, usually by reducing the gain of louder parts of the track above a certain threshold, and then restoring overall level, which brings up the lower sections. So the loudest parts of the music end up at the same level, but sound compressed, which, if done well, is a good effect, one which mimics the protective aspects of our own hearing. And the lower levels are a bit louder, a bit more prominent, so people listening in noisy environments or at lower overall levels can still hear the quieter parts of the song clearly, without straining or without those sections being drowned out by ambient noise. Even in some of the louder sections of the song, some background parts that fall in between the loud beats or other louder sounds, may be brought up a little bit by compression, making the mix overall sound fuller without being drastically obvious. The key to this is getting the balance right. With a full, wide dynamic range, like live music, smaller playback systems and less than ideal listening environments may get in the way of enjoyment of the music. But too much dynamic range reduction, where the difference between the softer and louder parts of the music is too small, will suck the life out of the music. Sudden loud moments, like the dramatic entrance of drums, will be anticlimactic. High-energy choruses will fail to draw the listener in if they're no louder than the mellow verse that preceded them. And even within a section, if the compression softens the punch and snap of percussive instruments, the thump and whack of the beat may lose its power to excite listeners and bring the crowd to its feet. Besides those aesthetic considerations, there are potential compression artifacts if the process is excessively or carelessly applied, like the infamous pumping and breathing, where the overall level audibly goes up and down when it should be steady, for a distracting effect. But when it's used well, compression can, in fact, help to glue all the elements of the mix together, keeping them in the forefront of the listener's attention and enhancing appreciation of the musical arrangement. Just as with EQ, any compressor can be adapted for mastering use, from basic DAW includes, to character models, to specialized designs. Compressors for mastering could be put into two basic categories: single band and multiband. Most normal compressors are single band designs. They affect a single frequency band encompassing the entire audible range of 20 Hz to 20 kHz. Multiband compressors are really 3, 4, or 5 compressors in one, each acting on a separate frequency band. The idea is that when you compress a track, a mix, with a lot of different instruments in it, as opposed to a single instrument, the compressor may be set to have a beneficial effect on one element of the mix, but then negatively impact the sound of some other instrument. The classic example is a kick drum in a mix. When a kick hits hard, a compressor will pull down the level. If the kick is alone, or if there are only other drums in that track, that's probably fine. But if the kick is part of a mix, and there are other instruments sounding, especially sustaining notes, then those instruments may be pulled down as well, causing the level of the rest of the mix to pump up and down with the kick. An unfortunate and amateurish sounding flaw in the audio. A multiband compressor would process the different frequency bands separately, so that when the kick comes along, most of its energy is in the lowest band, so only that low band compressor pulls down only that range. Sustaining notes from other instruments in other higher frequency bands are unaffected, and the dynamics of the rest of the mix are preserved properly. But besides basic problem solving like this, Multiband compressors are powerful tools in experienced hands. They can be used to dynamically shape the tonal balance of the mix and more selectively apply compression only when and where it's needed, pumping up the mix more subtly without undesirable effects for a more natural-sounding push that preserves more of a sense of dynamics even while those dynamics are being well controlled. So I'm going to focus primarily on multiband compression here. Coming up, I'll go over the basic layout and operation of a typical multiband compressor, and we'll look at a couple of different models in action. A multiband compressor is several individual compressors in one, each acting only on a particular frequency band. If you didn't have one, you could make your own. In fact, it's a good way to understand how a multiband is put together. To assemble your own multiband, you'd insert the same compressor in several channels and filter each channel to pass only a certain frequency range by constructing your own crossovers. I'll quickly set up 3-band multiband compression here in Pro Tools, which doesn't come with one of its own included, although we do have a nice one available for separate purchase. I'll leave the mix on its original track for as-is comparison, and copy it to a second track with a single-band compressor, also for comparison. To set up the multiband compression, I'll duplicate it again on these 3 tracks and insert the same compressor in all 3, bypassed for now. Then, to divide up the frequency ranges, I'll insert high and low pass filters. A low pass filter here will remove everything above 100 Hz, making this the low band. A high pass filter here will remove everything below 10 kHz, making this the high band. I'll set up band pass filtering in the middle track, low pass at 10K, high pass at 100 Hz, and now we have the mid-range band. If I play all 3 together, they sound identical to the original. But if I solo each in turn, you can hear which frequencies will be processed by the individual compressors in my homemade multiband.
Look at my face.
Now I'll set the same settings in all the compressors. I'll do this while listening to the track with the single band compressor, and I'll adjust it for noticeable compression, but not too much effect. Then I'll duplicate those settings on each of the multiband channels and group them. Now, when I compare the single band compression to the multiband compression with the same compressor model with the same settings, I can hear a noticeable difference. With multiband compression, the sound is brighter and fuller. Why is that? Well, most of the energy in music in a typical mix is in the mid-range, with much less in the lows and highs. So while the mid-range crosses the compression threshold easily, the low and high ranges barely touch it, resulting in much more compression, much more gain reduction of the mids, and much less gain reduction of the lows and highs, producing this characteristic smile curve with the bass and treble emphasized. But of course, you can adjust threshold, along with all the other compressor controls, independently in a multiband compressor, giving you the power to shape the sound dynamically. Here's a proper multiband. This is Logic's Multipressor, a 4-band compressor that's included with the program. As you can see, you can adjust the crossover points between the bands and the static level of each band as well. Even if you weren't compressing, that means you could use it as a semi-parametric EQ. But a multiband compressor can be more powerful as a dynamic EQ, where the level of each band changes depending on how much gain reduction occurs from moment to moment in each band. You have individual controls for each band for compression threshold and ratio, attack and release, and detection characteristic, RMS or peak. Like a lot of multiband compressors, this one also has individual per-band controls for additional dynamic processing, in this case expansion, but I'll set that to have no effect and just focus on compression here. In addition to the individual makeup gains for each band, at the top there's also a final overall makeup gain. This is a typical layout, including the metering, showing gain reduction per band, as well as overall output level.
I see her look at my face. Seems like I'm in another world.
If I switch to Isotope's Ozone 6, you can see that their multiband compressor is very similar in layout. Threshold, ratio, attack, release, and makeup gain per band, as well as overall gain. Instead of an extra expander, this one has an extra limiter per channel, and also the option for individual band parallel compression. A nice touch. Coming up, I'll run some music through these multibands, and we can see them in action. I've set up a mix running through 4-band multiband compression, the built-in Logic multipressor on one track, and the multiband in Isotope's Ozone 6 on another track, just for comparison.
I see her look at my face. Seems like I'm in another world.
This mix is pretty well balanced, but it could be maybe a little more open in the top end, and maybe the guitars and harmonies could come through a little more prominently. Multiband compression should be able to handle that. I've divided the frequency ranges at 110 Hz, 1200 Hz, and 11 kHz. The first band will isolate the bass, affecting primarily kick drum and bass guitar, and the overall weight of the mix. The second will contain most of the music, the fundamental frequencies for the instruments and voices. The third band is set up to be a kind of presence band. Harmonics in this band will determine the color of the track. A lot of time, I divide this one at a slightly higher frequency, maybe around 2 or 3 kHz, but for this song it seemed to work best here. Adjusting this band can contribute to the sense of openness and presence. The last band is high treble, air. Tweaks here can add brightness, especially to cymbals, which often keep time throughout the tune. I'll start off with the same settings on all 4 bands, adjusting different bands as needed. I'm going to leave the makeup gains at unity to start. Usually I prefer to adjust the levels of the bands dynamically with different threshold settings, which I feel is a more subtle way to rebalance the track, since it can follow the dynamics of the song. Now, ratio is an important setting. When compressing a full mix, even with a single band compressor, it's common to use much smaller ratios than you would on individual instruments. Since everything is being affected when there's gain reduction, you want it to be smooth and subtle. Typically, that means ratios of around 2:1 or lower. I usually use from about 1.4:1 up to around 2:1, depending on the mix. Here, I've set a ratio of 1.8:1. Attack and release settings will depend on the music and the characteristics of the compressor itself. I'll start with a fast attack of about 2 milliseconds and a medium to slow release of 500 milliseconds. The slower the attack, the more transient energy you'll let through. And the faster the release, the more fullness or bloom you'll get. If you're not careful, this could become undesirable pumping. For this song, a faster release seemed to make the mix a little too dense, and a slower one didn't add quite enough subtle thickness. Attack time is often set a little slower for lower frequencies, to let a little more of the low-frequency transients through, preserving a bit more punch. although keep in mind that this will also be affected by the final brick wall limiter. With very low ratios, it's common to also set a fairly low threshold. This will result in gain reduction being applied very gradually as the music gets louder, making the compression smoother rather than hearing it kick in more abruptly on louder notes. I'm starting with minus 24 dB here, which is not that low, but this mix is fairly even and level and doesn't ever get really quiet, so I think that's a good starting point.
I see her look at my face. Seems like I'm in another world. I see her.
Now, so far, this seems good. The multiband is bringing out the rhythm instruments in the verses and adding some fullness to the choruses. But I feel the kick drum has lost a little punch in the choruses, so we'll increase the low band's threshold for a little less compression on the kick. That, along with the slightly slower attack, should help keep the kick punchy, as well as add just a little heft to the mix overall.
I see her look at my face. Seems like I'm in another world.
I like the hi-hat in the verses, but the ride in the choruses may be just a bit too upfront. If I brought down the highs with a static EQ to tame the ride, the hi-hat would lose as well, so we'll adjust the level of the high band's threshold, lowering it so, hopefully, it'll catch the louder ride in the choruses and keep it in check, but still let the softer hi-hat through in the verses.
I see her look at my face. Seems like I'm in another world.
So, once I adjust the overall makeup gain to match the track's level in the louder choruses, here's what we've got.
I see her look at my face. Seems like I'm in another world.
The compression is filling out the mix, bringing out the rhythm instruments and vocal harmonies, and adding a little heft and sparkle as well.
I see her.
I tried the same settings in Ozone's multiband, which sounded a bit more aggressive.
I see her look at my face. Seems like I'm in another world.
So I bumped up threshold and release a hair, and lowered ratio from 1.8 to 1.6 to 1 for a more similar effect.
I see her look at my face. Seems like I'm in another world.
So this particular example used the multiband to add a little gentle push to the mix, without sacrificing the punch and snap of the drums. But remember, there's going to be another mastering stage that will also affect dynamics, the final brick wall limiter. While compression, either single band or multiband, can be employed to shape the dynamics and tonality of a mix, the other dynamics processor used in mastering, the brick wall limiter, is simpler to implement and yet generates more controversy than any other mastering adjustment. More on that later. A brick wall limiter is an extreme form of limiter, really only fully implemented digitally, that has an effective ratio of infinity to 1. That means nothing, no signal whatsoever, can exceed the threshold. Technically, this is accomplished by building a look-ahead feature into the limiter. The audio signal passing through it is delayed by a few milliseconds, giving the limiter the ability to look ahead at the incoming audio, and when it sees an over, a level above threshold, it has enough time to be ready to reduce the gain without the leading edge of the signal slipping through, causing a momentary overload. And it works well, but it does add some latency, anything from a few milliseconds up to 20 or even as much as 50 milliseconds delay, which should be compensated for by the DAW's automatic plug-in delay compensation feature. Now, the reason for such drastic limiting was, originally, simply to prevent digital overs, where the signal would exceed the absolute maximum digital level, 0 dBFS. That's full scale at the top of the meter.
Seems like I'm in another world.
Since digital overs can produce nasty clicks or pops, it's important they be avoided.
Seems like I'm in another world.
In fact, some playback devices have problems with signal levels that hit 0 dBFS, even if they don't go over it, so it's standard practice in brick wall limiters to set the maximum output level to just a hair less, most typically minus 0.2 or minus 0.3 dBFS.
Seems like I'm in another world.
That's usually enough to ensure clean bounces and playback, but sometimes it's set a bit lower, closer to minus 1 dBFS. I'll cover the technical reason for that in a later tutorial. These are some typical brick wall limiters. If all you wanted to accomplish was to simply prevent digital overs, you could do the following. Normalize the track, which will raise or lower the overall level of the entire file so that the loudest parts of the wave reach 0 dBFS but don't exceed it. Then set the maximum output level or output ceiling on a brick wall limiter to, say, minus 0.3 dBFS. And you'd be good to go. But, as you probably already know, brick wall limiters are not just used to protect against digital overs. They're also employed to raise the overall level of a track without incurring digital overs to a higher level than could be achieved by simply raising the fader level or normalizing the file. That's why brick wall limiters are also known as loudness maximizers, and for most people nowadays, that's become their primary function. Even going back to the vinyl era, artists and record labels have always felt that if a song's level is louder than other songs, on the radio or nowadays in a stream or playlist, then that song will jump out and grab the listener's attention. And the flip side of that is, if a song is much quieter in overall level than other songs that precede it, it'll seem lacking in energy, and listeners will ignore it or lose interest. Now, there's some truth to that, especially about lower-level songs seeming anticlimactic, and listeners having a negative reaction to the lower energy level, even if the song is something they'd otherwise like. So it's a good thing that brick wall limiters can allow for a higher overall level. But, and it's a big but, if they're taken too far and overused, levels pushed up too much, it'll have a negative impact on the quality of the mix and the listenability of the song that will undermine any potential benefit from the hotter level. And it's widely felt in the industry that current practices often, routinely, take things too far. The race to make every song as loud or louder than everything else has been dubbed the loudness wars, and as I mentioned earlier, it's been the subject of endless debate over the last 20 years, as digital technology allowed for ever-increasing levels. So what's the real story here? How does the technology of brick wall limiting allow levels to be raised to these heights, and what are the potential pitfalls of overdoing it? I'll cover that in the next chapter. So how do brick wall limiters make it possible to raise the overall level of a mix so much higher than otherwise without overloads? Well, to understand the technical side of this, you have to be familiar with the difference between average levels and peak levels in audio waves. Here's a wave of a typical mix. And another of a drum track. both, you can see that there are very brief sections at the beginnings of notes where the wave is much louder momentarily before it settles into a lower level. These are impact transients, basically bursts of noise at the beginning of a percussive sound, the attack of each note. They correspond to impacts like the stick hitting a drum or the hammer or pick striking a piano string or guitar string, respectively. On the other hand, non-percussive sounds without sharp attacks may not have these brief transient impacts, as you can see in these waves of voices singing ahs. Attack transients usually last only a few milliseconds, typically 10 to 20 milliseconds at most, before the sound settles down into the rest of the note, the body or sustained portion of the note. The level of the transient is the wave's peak level, and the steady level of the body, the sustaining part of the note, is the average level. Transient peak levels can be as much as 10 to 20 decibels louder than the average level of a sound, but because they're so short in duration, that louder level doesn't register consciously with our hearing. How loud a sound is perceived to be, compared with other sounds, is determined instead by the sound's average level. The brief transient peak is perceived as impact, rather than loudness. That thump you feel in your chest from a loud, sharp kick drum, for example. So, two audio recordings could have the same perceived and actual average loudness level, but if one also has transient peaks, it'll register a higher level on the meters and would overload sooner if the average level of both was gradually raised. This means that, say, a lightly played ballad, without drums, could potentially be raised to a much higher level than a high-energy, full-band rock song, since the drum transients in the louder performance would hit maximum level, 0 dBFS, sooner, giving rise to a situation where the quiet ballad might blow the rock track away in terms of level. If the rock song played first, when the ballad came on, it might send listeners running for their volume knobs, distracting them from the song.
She doesn't say a word. Some feelings defy boundaries. They glow hot and are almost blinding.
If the ballad played first, and the listener adjusted listening level for comfort, when the rock song came along with its lower average level, dictated by the transient peaks, it would be a letdown instead of a boost in energy.
I feel my way slowly, telling myself she comes here every day.
The listener might react to this letdown by reacting negatively to the song itself. But engineers realized that if you carefully limited the level of just the transient peaks in an audio wave, you could then raise the average levels of the file without hitting the overload point so soon, allowing for a much higher average level, but at the expense of some of the music's transient punch. When brick wall limiters came along, it became possible to do this reliably to a much greater degree than ever before, and since digital audio has no inherent limitations for average level, like analog does, a song with its transients reduced this way can have its average level pushed all the way up to maximum, 0 dBFS, giving rise to the possibility of much louder recordings than analog could ever handle. But the technology of brick wall limiting does not rewrite the laws of physics. There's a trade-off. You can shave off about 6 dB of transient level without it really being noticeable. There may be a little less sense of that chest-thumping impact, but the music will sound pretty much the same, only the audio file can now be made up to 6 dB louder, safely, without overloads. But if you push harder, the loss of transient impact will become noticeable. Percussive instruments like drums may start to sound like the drummer's not playing as hard, like a more lackluster, lower energy performance. And if you shave off even more transient level, the drums may start to sound downright mushy. In extreme cases, almost more like brushes and sticks. In a mix, very often the level of the drums against the other, more sustaining instruments in the arrangement may be dependent on those transient peaks, making the drum cut through a dense mix. If those peaks are reduced too much by brick wall limiting, then the drum part may recede into the mix. Again, in worst-case situations, I've heard a kick drum that was barely cutting through in the verses almost completely disappear in a denser chorus. Sure, the track was louder than a lot of other songs, but I'm sure the drummer, and maybe the artist, wasn't happy about how the beat was compromised to achieve that loudness. Pushing average levels up this way means that the normal dynamic variations of the music will also be compromised. As the difference between maximum average level and maximum peak level is reduced too much, any sense of musical dynamics is also being lost. 24-bit digital audio has a potential dynamic range of 144 dB, but many commercial releases have a dynamic range of barely 6 dB. If everything is as loud as possible, then how do you make a chorus stand out or highlight the dramatic entrance of a solo instrument? Mixes become just one long drone, and this leads to listening fatigue. Listeners switch off the music sooner because their ears are tired from the non-stop assault of loud, louder, loudest. Current practice these days has pushed levels until it's become common for artists and labels to request a level that exceeds that point of no return, making unhappy mastering engineers struggle to try to achieve it, but still manage to not excessively compromise the listening experience. This is why there's so much discussion and hand-wringing about the loudness wars, and anyone who takes on a mastering job is going to find himself right on the front line of this debate, often being pulled in two directions: to make the final master sound as good as possible, but also to make it as loud or louder than something else. And unfortunately, after a certain point, these two goals become mutually exclusive. So let's see brick wall limiting in action and listen for these effects. Next up, I'll run a mix through brick wall limiting, and we'll see just how far we can push levels and what the effects of that can be. Okay, I've got a mix loaded on 3 tracks here. All 3 have a multiband compressor with the same settings used a couple of videos back. In this top track, there's no brick wall limiter, just the compressor, which is set to maintain the same level as the original file. We'll use this to compare the audio without limiting to the brick wall limited version as we apply the processing. Without limiting, the loudest peaks here top out at about -1 dBFS or so. About as loud as the audio can get without digital overloads. Mastering engineers sometimes request that the mix level top out no higher than -3 dBFS to give them some breathing room, but as long as it doesn't go over 0 dBFS, it should be fine. Digital overages in the mix itself might cause the limiter's peak detection to not work as well as it should, so they should be avoided. The next track has the same Ozone multiband with the same settings, but it follows it with Ozone's peak limiter named Maximizer, as in loudness maximizer. Everything's identical except for the application of the maximizer, the brick wall limiter. The third track is set up just like the second, but with the Logic multipressor and their brick wall limiter, the adaptive limiter. I'll just focus on tracks 1 and 2. All the track faders are at unity gain, as they should be at this stage. This way, as we apply limiting, we'll see just how much additional level we can add by limiting the transient peaks in the song, which, as you can hear, are mainly the kick and snare. I've set the output ceiling to -0.3 dB, and as I lower the limiting threshold, the gain is automatically increased by the same amount. That's how all brick wall limiters work, whether the control is labeled threshold or gain. At around -6 dB, 6 dB of gain, I'm just about to the point where the limiting is still pretty much transparent. As I A/B against the original version, you can see how much additional gain I've added.
I see her look at my face. Seems like I'm in another world.
The mix, the drums especially, still sounds punchy, and everything is fine. But this level is probably about 2 to 3, maybe even 4 dB lower than the very loudest releases out there, and sometimes a nice, transparent mastering job like this will be returned with a request for more level. I can push this particular mix another 2 dB or so.
I see her look at my face. Seems like I'm in another world. I see her.
It still sounds good, although if you listen closely, you can hear that there's a little softening of the drums and a little congestion just beginning to develop. But it still sounds okay, and now it's probably just about loud enough to pass muster, even with level-obsessed artists and labels. But if even more level is requested, then you'll start to hear a more negative impact on the mix. The drums start to sound weaker and recede from the forefront, to the detriment of the arrangement.
I see her look at my face. Seems like I'm in another world. I see her.
This would be obvious against the original mix track, but the increase in level is so distracting that it may be glossed over as the ear adjusts to the new, less crisp, less punchy reality.
I see her look at my face. Seems like I'm in another world.
To really hear just how much the limiting is affecting the quality and integrity of the mix, you want to match the levels of the original track and the limited tracks so you won't be distracted by the level difference, and you can really hear if the limiting is making it better or just louder but mushier. This is easy. Just pull down the level of the limited channel's fader by the same amount you've set with the limiter threshold itself. Now the body of the music, the average level, will be at the same level with and without limiting, and any effect on the transients and the balance of the percussive elements of the mix will be obvious. I'll start at -6.
I see her look at my face. Seems like I'm in another world.
As you can hear, the limited mix sounds virtually identical to the other. The drums, kick and snare, retain all their snap.
I see her.
At -8.5, you can hear a little softening of the drums, but they're still punchy enough. Listen especially to the kick in the choruses. There's a little less thump, but it's still holding its own.
I see her look at my face. Seems like I'm in another world. I see her.
But at -10, you can hear the drums soften excessively, changing the mix. To my ears, this is too much for this song, even though I often hear that much limiting applied to commercial releases.
I see her look at my face. Seems like I'm in another world.
At this level of compression, once your ears become accustomed to the artifacts of brick wall limiting, you can also hear that a little congestion, distortion, has crept in.
I see her.
If I switch to the Logic limiter, it's pretty much the same story, with the same effect at more or less the same degree of limiting. Fortunately, the trend toward unbridled loudness maximizing may be on the wane, at least according to the buzz. More releases are coming out with average levels a few dB lower, closer to the point where acceptable transparency can still be maintained, and there's a movement afoot to try to standardize more reasonable maximum average levels. In the meantime, a gentler hand on the limiter threshold and careful listening at this stage can help you avoid compromising a mix with too much of a good thing. Next up, there's one more technical issue I want to cover regarding level and digital overs. The level meter you're looking at is one of Logic's built-in metering plugins. It's set to show both average level in the lighter blue and peak level in the darker blue. The track is the same one from the previous video, with Logic's multipressor and brick wall adaptive limiter, with its threshold set at -8.5 dB for 8.5 dB of gain. As you can see, there's about 10 dB of difference between average level and peak level, which is just about enough to maintain a reasonable sense of dynamics and impact, despite the 8 dB of transient reduction. At the top of the peak meter, you can see the brick wall limiter holding the level at the output ceiling setting of -0.3 dBFS. Now, while in most cases this provides a reasonable assurance that peaks will remain safely below 0 dBFS, this isn't necessarily always the case. The reason for that is fairly technical, in a counterintuitive digital theory kind of way, but I'll go ahead and explain anyway. It's true that the digital levels of this finished, rendered, and mastered audio file will be made up of samples all no higher in level than -0.3 dBFS. But when those samples are converted back to an analog wave for playback, there's a possibility that levels may slightly exceed that ceiling. This means that any slight overages are actually a conversion artifact of the D to A, digital to analog converter. Digital meters can't pick up on this because if these overages happen, they don't actually occur in the digital domain, they happen on conversion to analog. However, digital meters can be designed to anticipate them and provide a reading that'll indicate the likelihood of such overages happening in some A to D converter's output stage. These overages are called intersample peaks, and if I switch that mode on in this meter, you'll see that the output levels occasionally read as slightly higher than -0.3. In this case, by up to around half a dB or so.
I see her look at my face. Seems like I'm in another world.
What causes this is the A to D converter's smoothing filter, the last stage of conversion to analog. As you know, the samples in a digital wave describe the wave as a series of steps, representing a normal smooth analog wave. When the digital representation of that wave is finally converted to analog for monitoring, the wave is smoothed out back to the normal smooth shape of all analog waves. When that occurs, the smooth shape of the wave may actually reach a very slightly higher level here and there than the actual level of the highest digital samples. This extra level is an intersample peak. The concern is that some converters may not handle this extra level cleanly enough, although in most cases, these peaks are so brief they'll probably pass unnoticed. But if you want to ensure the highest quality, cleanest signal output, you can lower your output ceiling based on this readout, eliminating any potential loss of signal quality. Here, lowering the ceiling by another half a dB to about -0.8 seems to be enough.
Seems like I'm in another world.
Pro Tools has an even more informative display. This is the same mix run through Pro Tools Maxim, which is their included brick wall limiter. Same settings here as in Logic. Their master meter shows a list of all intersample peaks can scan, find the highest level, and then reduce the output ceiling by the difference between its current setting and the maximum estimated intersample overage. As you can see, it's about the same setting as in Logic.
Seems like I'm in another world.
And that takes care of it. Now, whether you want to go to the extra trouble of detecting estimated potential D to A intersample peaks and compensating for them is up to you. Many digital masters were made before people became widely aware of this phenomenon, and they play fine through most any converter, at least any relatively decent modern converter. And a lot of people are still not aware of the potential for intersample peaks, and their digital files play just fine, with traditional ceilings like -0.3 dBFS. But if you wanted to be extra careful, and you don't mind losing an extra half a dB, up to maybe a dB at most of level, then you could just set output ceiling to -1 and not worry about it. You'll probably be fine either way. If the loudness wars ever finally go away, then maybe the industry can standardize new levels that factor in both consistent, reasonable average levels and extra headroom for these peaks. Maybe someday. Next up, I'll take a look at MS, mid-side processing, as it can be applied in mastering. MS, or mid-side processing, is an alternate way of addressing a stereo file that goes way back. It's the same approach used in MS stereo microphone recordings. Instead of a left channel and a right channel, the stereo signal is made up of a mid signal, everything in mono, and a side signal, which is the difference between the left and right sides. For a stereo mix, this allows you to process the mid elements in the center of the mix, typically lead vocals, drums, bass, separately from the other elements of the arrangement, which are usually panned, to some degree, off to one side or the other. The side signal is primarily made up of these instruments, along with ambience and reverb, any component of the mix whose signal would be different in the left and right sides. Many plugins, especially mastering-oriented plugins, will convert a standard left-right stereo signal to MS, but you could even do it yourself. You would duplicate the stereo mix on 3 channels. One would be the mid, switch to mono. The other 2 would make up the side signal, the difference between left and right. You'd flip the polarity of one side, here the right, set this channel to mono, and pan it to one side, left, to preserve the same left-right orientation. You'd do the opposite with the other side channel, flip left polarity, mono, pan right. I've routed them through a stereo bus just for convenience. The routing doesn't affect the sound. That bus now contains the side signal. I've also routed both mid and side signals through another stereo bus, again, simply for convenience. When the mid and side channels are combined, you hear the mix normally.
She comes here every day. She doesn't say a word. I see her look at my face.
If I mute the sides, you hear the mix in mono.
Comes here every day. She doesn't say a word.
If I do the opposite, you hear just what's on the sides of this mix, just the difference signal. Anything in the center that's common to both left and right is missing, thanks to the polarity inversions. Notice how the bass and kick are missing. They're pretty dry. The other centered instruments, snare and lead vocal, have a lot of reverb on them, which is a stereo signal with differences in the left and right. So the reverb for the kick and snare is audible, even though the main, dry, mono signals are absent. By the way, this is how those cheesy vocal eliminator boxes used to try to strip the vocal out of commercial recordings, so you could go all karaoke with the track. The most basic kind of processing you can do with this is to adjust the balance between mid and side signals. As you increase the level of the sides, above the level of the mid, the mix gradually widens.
It doesn't say a word.
As you reduce the level of the sides, the mix gradually narrows, eventually to mono.
Seems like I'm in another world.
Small adjustments can subtly narrow a mix that might have too many hard pan tracks. Or widen one that's too focused in the center, bringing out the side pan background tracks a little, or increasing the level of the ambience.
It comes here every day.
Just don't go overboard.
It doesn't say a word. I see her look at my face. Seems like I'm in another world.
Now that you have the center, the mid, and the sides separated, you can process them independently. For example, you might want to compress the drums and vocal a bit, but not apply so much compression to the guitars and reverb, where it might make the mix sound too ambient and washed out. Inserting a compressor, any type, in the mid signal path only, you can do this easily. I'll put the same compressor on the regular stereo left-right signal. You can hear how the same setting squashes the entire mix too much, but works better when it's not hitting the sides so hard.
It comes here every day. She doesn't say a word. I see her look at my face. Seems like I'm in another world.
Or you might want to EQ the sides, where there are cymbals and doubled acoustic guitars, brightening them up a little, without making the snare and vocal too thin or sibilant. Again, here's the same EQ settings on the regular left-right version of the mix, and applied just to the sides, where it adds nicely to the hi-hat and ride without noticeably affecting the voice and drums too much.
It comes here every day. She doesn't say a word. I see her look at my face. Seems like I'm in another world.
You won't usually have to go to the trouble of creating your own MS Matrix. I just did it here to clarify how the process works. Many plugins have built-in options for MS processing. Even basic EQs, like Logic's included channel EQ, sometimes offer it. Vintage emulations may have MS options. Mid-side processing is applicable to the way grooves are cut in a vinyl record, so a lot of classic vintage analog gear allowed for it, like the famous Fairchild compressor. And of course, most mastering suites have MS capability. Ozone lets you switch to MS processing in all the modules where it would be appropriate: EQ, Dynamics, and Exciter. Mid-side processing can be a valuable tool in mastering, another extremely useful option in the mastering engineer's toolbox. Coming up, I'll start to wrap up, taking a look at some of the more technical aspects of mastering. When the processing is done and the songs are ready to be bounced or rendered as finished audio files, then it's time for a last-minute technical check to make sure there are no issues that have escaped notice. Many DAWs, and pretty much all mastering suites, have a number of metering plugins to help with this. And there are plenty of third-party metering plugs as well, some of them available as freeware. There are a number of things you'll want to double check before committing to the mastered versions and doing the final bounces. You should be sure to check the beginning and end of the files for any clicks, excessive dead space, or other edit-related problems. If there's going to be a fade, you'll want to do it at this stage. Traditionally, fading out at the end of the song employs an S-curve, which will give the smoothest sounding fade. An S-curve will start off the fade slowly, speed up a little bit, and then slow down again just as the audio disappears into silence. This way you don't hear the file suddenly end as it's fading. It's the smoothest transition, and it's the way any mastering engineer would do it. If you're mastering a collection or album, you'll want to check that the average levels of all the songs are about the same. If some songs are musically quieter and others louder, the consistent element among them would usually be the lead vocal. The best approach is to make sure that the level of all the lead vocals is not only around the same, but what variations there are musically appropriate. So a vocalist on a quiet ballad might be a little lower in level than a screamer in an up-tempo song. This means you shouldn't automatically make all the songs as loud as the maximizer will let you. The most appropriate musical level balance between songs is preferable. As a reality check, if you have some commercial releases in the same genre loaded up as reference tracks, you might now want to briefly check the levels and overall balances of your songs against them, just to make sure you haven't gotten carried away or lost track of industry norms. It's the last chance to glance at the average versus peak level meters to make sure you're okay with the effects of the compression and brick wall limiting. If the difference is less than 6 dB between average level and peaks, well, you still have a chance to revisit your dynamic processing and maybe pull back a little. If you have any doubts about the tonal balance, if you think you hear any peakiness at certain frequencies, for example, and you want to make sure it isn't in the audio file, you could check a spectrum display to see if any frequency anomalies are visible, like obvious peaks or dips that might have crept in to compensate for room response irregularities. You'll want to check the stereo aspect of the songs to make sure there are no left-right imbalances. If you're sitting even just a little off-center, it would be easy to miss it if a song was pulling a little to the left or right. The instruments that should be centered were a little off-center. I have the imaging meters open here from both Ozone and Logic. Ozone's Vectorscope is part of their imaging module, which allows for MS-type processing, but I have the processing off so we can just see the displays. The Lissajous pattern display, which you can see here and in the Logic plugin as well, shows stereo information and balance. If the mix was a little off-center, it would tilt to the left or right. I'll simulate that to illustrate. A correlation meter, displayed vertically in Ozone and horizontally in Logic, shows left-right difference. At +1, it would indicate no difference between left and right, or mono. At -1, it would indicate left and right channels out of phase, or in reverse polarity. Normal stereo would be somewhere between 0, center, and +1. It's very important to always check the audio in mono before finalizing it. There are plenty of places, restaurants, clubs, cars, where music may be played in mono, and some stereo effects and processes might reveal major problems in mono playback. Switching to mono and checking the songs is a must. Just don't forget to enable full stereo again when you're done. And of course, the last thing I do is, if possible, take a brief break and then play through the songs, listening carefully for anything problematic that might have escaped notice up to that point. Once you're satisfied, then it's time to bounce down to the final stereo masters. I'll continue with that in the next chapter. As I mentioned at the beginning of the course, all professional audiophiles are currently 24-bit resolution. You may know that DAWs process the audio at a higher resolution, 32-bit floating point resolution, but the finished WAV files will be 24-bit, with one exception. Even though downloads and streaming are gradually taking over as the primary forms of distribution for music, CD sales are still a significant component, and CDs, the oldest format still around, have always been, and always will be, 16-bit. So while your main master audio files will be 24-bit WAV files, if the music will be distributed on CD, you'll need to make another 16-bit WAV to be used as the master for CD duplication. And this involves an extra step. In most cases, the difference between 16-bit CD audio and 24-bit audio is unnoticeable. But to remove the last little bit of the extremely low-level digital quantization distortion that's still present in 16-bit audio, an extra process is applied as the last step in making a 16-bit master. Random noise, called dither, is added to the audio at an extremely low level as the final bounce is done. This eliminates any vestige of distortion that falls within the range of human hearing. For a much more detailed explanation of all this, check out the Audio Concepts series Recording Tools course. Since this digital distortion is below the range of human hearing in 24-bit audio, there's no need to dither it, but any 16-bit CD masters still need to have it applied. There are two ways to add dither. One way is via a plugin, which would have to be the last bit of processing applied. That means no other changes after the dither, not even a fade-out or a channel fader set to something other than unity gain. Those settings should be made in the channel fader for the song, and the dither plugin added in the master fader, which must stay at unity gain. If there's a noise shaping option, well, this is just EQ to make the dither work better. I'd turn it on. Any noise shaping type should work fine. You can see a couple of dither plugins here in Pro Tools. You notice the dither is only implemented for resolutions below 24-bit. The other way to add dither is via an option in a bounce to disk dialog box. This is easier because you sidestep any questions of inserting the plugin in the right place. The song is bounced and the dither is added, and you're good to go. You can see the same options here in Logic's bounce dialog. Power and UV22 are just different brands of dither and noise shaping. Either will work. The power options are optimized for different types of mixes, wide or narrow dynamic range. If there's any doubt, I use the middle one. And that's it for dithering. I'll finish up with a brief discussion of audio file formats and metadata. In the beginning of the course, I mentioned that all professional masters are full-quality linear PCM, pulse code modulation, audio files. These are large files, but they provide the highest audio quality without compromise. But PCM is not a file format, it's a file type. The formats of PCM files are either AIF or AIFF format, or WAV format. Many, many years ago, AIF was the MAC standard and WAV the PC standard, but now both are universally used. That said, there is a transition happening to the newest version of the WAV standard, Broadcast WAV, or B-WAV, as the one universal PCM audio file format. I'd recommend bouncing all masters to B-WAV. Even if it only says WAV in the dialog box, nowadays it'll be Broadcast WAV. Of course, you all know there are other audio file formats out there, these days even more widely distributed than PCM files. Occasionally, you may run into what's called lossless audio files. These are files that have been squeezed down to about half the normal size without any loss of signal quality. They just have to be decoded before you can play them. FLAC files are probably the most common, although Apple also has a lossless codec which you can access through iTunes or QuickTime Player. But much more familiar are probably MP3 files and MP4 files, also known as AAC files, which employ data reduction algorithms to make the file sizes smaller for greater convenience in streaming and downloading. These data-reduced, or data-compressed, formats range from about 1/5 to 1/10 the size of the same PCM WAV or AIF file. This chart shows the relative sizes of the same file in these different formats. But the processing used to reduce the file size so drastically deliberately compromises the audio quality. Perceptual coding relies on the ear's internal working to mask the loss of audio data, but this isn't 100%, and even the best of these smaller format files always sound a little thinner, more opaque, and less detailed than the original PCM masters they're derived from. Even though all your mastering efforts will end up as PCM audio, you'll still have to supply low-res versions for a variety of situations. I'm not going to go into great detail on this here, because it falls more in the realm of distribution than mastering, but I'd suggest that, when you have to create low-res versions, make them the best resolution possible. MP3s and MP4 AAC files are described by their streaming data rate. Higher rates mean slightly larger files with slightly better quality. An MP4 AAC file is probably a little cleaner and fuller sounding than the same size MP3, and 256K MP4s are a good choice. That's the current format of all the audio files on the iTunes Store. Apple even has a program called Mastering for iTunes that offers guidance and help in creating the best possible audio quality in that format for iTunes distribution. Check their Mastered for iTunes page for information and software downloads. The other topic I want to just briefly mention is metadata, the text data that's embedded in audio files. Again, this falls more in the realm of distribution than mastering, and this course is focused on audio processing and sound, and not marketing. But since metadata is sometimes added to the file at the tail end of a mastering session, I'll just touch on it a bit. Probably the most common type of metadata is the ID3 tags that describe the song: title, album, artist, date, etc. The information you see, and can add, in iTunes and other audio players. What I wanted to mention is a type of metadata that's particularly important if the audio will be commercially distributed: ISRC codes. These are codes that identify each individual audio recording, and they're used by performing rights organizations to track sales and radio play to make sure that the rights holders are properly reimbursed for their work. Some mastering suites, if they address distribution issues, might include the option to add these codes, so if you run across this, you'll know what it's about. The code has to be obtained for a fee via a website like usisrc.org, and can then be used to uniquely identify individual recordings. Again, this is not the focus of this course, so that's all I'm going to say on them. If you're doing mastering work and you find yourself getting involved with this distribution stuff, all the information you need about ISRC codes can be found on these websites. So that's it. I'll wrap up briefly in the last chapter coming up. So that's the end of this course on mastering in the box. For anyone who needs to take on that final stage of production, I hope this has provided some useful information and some helpful suggestions for approaching the black art of mastering. When I first tried my hand at mastering, after recording and mixing for many years, I found it was a bigger adjustment than I was expecting. I had to not only learn the specific tools and practices, but I found I had to retrain my ears to listen differently, for the small details rather than the big creative picture. While the tools were familiar enough and easy enough to get a handle on fairly quickly, it took me quite a bit longer to develop my ear for detail, to really embrace the whole less is more philosophy that infuses the mastering process when it's done at the highest level. So, I hope everybody who's just jumping into mastering will enjoy the process of adding that final touch of quality to their recording and mixing efforts. And even if, like me, you find yourself overdoing it at first, with today's powerful mastering tools at your disposal, well, your ears will come around, and then you'll start getting the results that'll make your tracks stand up to anything out there. So, happy mastering.